I guess a good point to start will be introduction. So could you describe what are you doing and what's your background?
So what I'm doing is that I'm currently a postdoctor working at a national lab called NIST at the Boulder, Colorado, and I'm working on building an atomic clock. Basically, it's an optical clock using atomic transition in the optical frequency domain to serve as a frequency reference. And this type of clock can be very precise because it's relied on the atomic transition, which at a few hundred terahertz level. So by counting the frequency precisely, you can convert it to the frequency units and or like use it as a seconds definition.
And before we jump into this topic more deeply, could you describe your background? So what did you study at university and how did you ended up at NIST?
My background is I did my bachelor in electrical engineering department back in Taiwan, and I always want to do experimental physics. And later I switched gear to do a master program at the same university, and that's the first time I enter atomic physics type of that's my first time start doing atomic physics, and then later after 1 year of after I finished my master degree, I served 1 year military service on some isolated island from mainland Taiwan. I spent a year thinking about whether I should start a PhD program to continue working on this research line or doing experimental physics. Uh, the answer was yes. I still think I think it's interesting. Then I apply for a position in Europe, and then start working in the Florian Schreck's group at the University of Amsterdam. And then after finishing my PhD program, uh, again another small thinking about whether I should continue. And I already have 6 years experience living in Europe. I decided, okay, I'm going to go somewhere outside of Europe, and then US is an option. That's why I ended up in the United States and continue working on still something similar, although oriented in different application research line, which that's where I started. I said, yeah, I'm working on atomic clock.
Yeah. And maybe let's go back a little bit. You said that first you were electrical engineer, and then after some thinking, you decided to move to the atomic clock or atomic physics community. And after you finish your master, after still some thinking, you decided to go to the experimental physics. So why did you do that? Because it's not like a absolutely straightforward transition from electrical engineering to the atomic physics. It's quite a shift.
To be honest, I consider them something actually quite similar. And I would even put myself not really the physicist, but maybe more like engineer, in a way that I enjoy solving problems. And sometimes experimental problems, I think it's a problem, and I enjoy solving problems. It's
You mean
related.
like technical? You mean like technical problems?
Well, sometimes I think experimental physics is, well, when you say technical, it's like there's no like physics ingredients inside. It's purely like soldering irons, doing something known actually. But what I consider like engineer is that you're actually trying to come up with a way to solve the problems you don't have a solution before. So in that aspect, I think I call everything engineer, actually.
Yeah.
Because you're actually trying to come up with a way, trying to solve a problem which you don't have a solution before. Yeah.
Yeah. And after you finish your PhD, you still decided to stay in the academia. But did you consider moving to industry, let's say back to the electrical engineering, or you really enjoyed being a physicist or scientist?
I'm open for options, to be honest, because I think sometimes, like I said, I enjoy solving problems. It doesn't have to be inside of academia, because there's problems outside there, which of course probably is more industry oriented. But like I said, you're trying to come up with the solutions for questions that you don't have an answer yet. And as long for industry, they do have problems that you don't have a solution yet, then I think I can contribute. That's
Yeah,
certainly my.
yeah, but I think there is quite a difference, at least in my perspective, between, let's say, electrical engineering problems. They're very challenging, they're very advanced, they're very important. And but on the other side, you have quantum community, let's say quantum technology, and challenges there. And even if both of these problems they're kind of difficult to tackle, but there is, I think, a fundamental difference between electrical engineering problems and quantum technology problems. And I think, like, do you enjoy specifically something in the quantum technology problems?
Uh, I wouldn't say no, because it's kind of it's a topic still in a fast developing phase, like other communities, to be honest. Like AI research is also a fast growing field, and I believe some, even including semiconductor industry, I think now we are at the age we are seeing still fast growing in semiconductor industry. So I don't want to limit myself
Yeah.
specifically like quantum community, because I enjoy this more than other community, like province in other community. Not really. So that's why I'm kind of, since I'm more or less kind of in the uh, switching phase, trying to figure out what's to do next. And
Yeah.
these days, I enjoy talking to people from different fields just to
Yeah.
get to what's actually interesting in your community, and see if I can get some inspiration, or actually get triggered to start also find it interesting. Then I might change field. And like I said, you're actually trying to target for interesting problems, trying to solve. And I consider myself that way, that well, I I enjoy thinking about things differently, trying to come up with new perspectives, and then once I consider that problem is interesting, and then I enjoy spending time trying to come up with solutions from different angle. That's what I enjoy doing. So that's, but quantum engineer, of course, because there's quantum mechanics behind, and probably people are more used to like prior quantum quantum physics, meaning that, okay, probably, do you think semiconductor community, do they have do you think they are actually, they don't have to worry about quantum mechanics? I don't
Oh,
think. Uh,
I think they do worry about quantum mechanics, but I think the degree to which they worry about is different, right? Because I absolutely agree that that electrical engineering is very important. It's a very challenging task, but I feel like when you're working on quantum technology, there is a little bit of romantic, in it. So because it's really like challenging problems, and there is no solid answer to most of the questions, and there is a huge room for you to grow, in a sense that you can go in any directions, and there is not much knowledge available or skills and expertise produced in the past years, right? So I'm not saying that electrical engineering is simpler or easier, but I feel like it's two different areas, right? And even if they're both technical and engineering problems, I feel like there is a difference if you're working as an electrical engineer or as you're working as a quantum engineer, right?
Maybe, but since right now I don't have much experience working in other community, of course, I don't think I have enough experience to make that statement, though. However, I think I I do believe that sometimes they are all questions, like they are all problems requiring similar like expertise, which you do have in quantum as a quantum engineer, but they also do have those expertise in like other community, and then looks different though, but to the essence, I believe they are basically similar.
Yeah, I mean, I agree that if you, let's say, good electrical engineering or quantum engineer and you switch the field, you can always grow and in a new direction. So I absolutely agree that if you have a good skills and knowledge and expertise in one field, for you there is no problem to switch. And yeah, as you said, you have to be open-minded about what you can do. I think it's a good approach. Yeah. So let's maybe go back to more scientific questions. You mentioned atomic clocks. Could you maybe briefly discuss what it is? I think you already started, but I interrupted you.
Yeah.
Sorry.
Well, atomic clock, basically, clock is you're looking for something doesn't change over time. For in this case, seconds. You're trying to have a good definition for seconds so that your time is basically same like my time. When I say that I spend 10 minutes talking to you, basically it won't be something like a year for you because we share the same kind of standards for time, how time passes. And when you're looking for something doesn't change over time, like the length of the time doesn't change over time. You're looking for some reference, which I do believe an atom provides you a natural. It's a natural candidate for you to sort of make use of it, because every same atoms, they are basically sharing the same kind of electronics levels under the same condition, and that's a natural candidate for you to use it for reference. And in this case, energy level, we use the energy level of the atom to serve as a transition, which we can convert it to, say, frequency and use that for time definition. And before atomic clock, we are using some transition which is at the microwave transition level. So that's already accurate enough for many of the daily applications, say current generation GPS, where you relied on atomic clock on a satellite, and then you can do the positioning based on that technology. But of course, when you're going to the next level of the precision, you're probably looking for something beyond microwave transition accuracy. Microwave only gives you something on the order of 10 to the 9, maybe, frequency reference. But if you're after something with better uncertainty, then probably you want to go to the next level, which is relying on optical transition. Basically, a few hundred terahertz, that's almost 6 order of magnitude, maybe higher than the microwave transition. So that's why currently we are trying to make the technology mature enough so at some point we can change the definition before we relied on this microwave transition to define the seconds. Now the next level is that we are trying to rely on optical transition to define the seconds, which apparently can give you order of magnitude improved uncertainty to define this.
And now we're talking about atomic clocks, and atomic clocks is kind of by definition is a quantum tool, quantum device.
I agree, yep.
And what makes it quantum? In a sense, let's say that there are other types of clock, but if I'm looking at the atomic clock, why it's quantum, what makes this device quantum?
Probably I would say it's because you're relying on some energy level, and you can consider it's a two-level system. And that's probably, I would call the starting point why we call it quantum, because we are using the energy level, which you can consider it's a two-level system, which we use it as for the transition. And then when you dig it deeper, to be honest, when you're trying to improve the clock, there are lots of like quantum mechanics start kicking in. For example, when the system start acting not like a two-level system. For example, when two atoms start to interact with each other, that affects the energy level maybe. So, and that's where those kind of interaction, you need atomic physics to describe them, to be able to understand them. To be able to understand them, then to be able to improve that, to avoid that effect affecting the performance of your clock. So to answer your question, the starting point is that it started with a two-level system, and you use that two-level system energy transition as a clock. But then you need to make sure, you need to ask the question that how perfect is this two-level system? Do atoms interaction affect this kind of the reference that you're using? And all sorts of quantum effects kicks in, and you're trying to understand them to be able to improve the performance of your clock. So yeah, that's why maybe to be more precise, people talked about quantum. That's why people probably start putting quantum onto clock.
And now actually my question is, if we can compare atomic clocks, which is quantum devices, to classical devices, which still clocks, I mean, whatever type this clock are. But if we compare quantum clocks and classical clocks, what's the main difference in terms of size, robustness, precision? Like, so what's the difference between quantum device and classical device?
Maybe talk about classical clock. What is classical clock in your opinion? What you would call classical clock?
Well,
I
mean, the most simple, it will be just my watch on my wrist. But probably it's right now technology is way more advanced than just the standard mechanical watches, right? So there are like more or less good clocks, but which are still classical, but they're just good clocks. Is it correct?
So you mentioned mechanical clocks that relied on, of course, the mechanical structures inside of your watch. Maybe some kind of the spring, which gives you the gear to kind of rotate in a precise way, so you can build a clock using that. But it's about, but before example, I mentioned spring, but the spring force, that's just, I guess, not precise enough, because for example, each clock, how can you be sure that each clock, they are built in the same way such that the spring force gives you same kind of the restoring force? So when you have two mechanical clocks, you can never be sure that they tick the same way, because they are built differently.
Yeah.
You agree. But if I give you 2 o'clock, both use the same atom as the reference. And like I said, atoms under the same environment, they behave the same, or like they share the same energy level, share the same property because they are the same atom. So that way you have more confidence to claim that this two clock ticks the same way compared to two different mechanical clocks. So to answer your question, classical clock, if you, what is your reference, right? For mechanical classical clock, if it's mechanical clocks, the reference would be all the mechanical structures inside of the clock, the spring force, that's the reference. And then you get the time based on the periodic motion of the tick.
Yeah.
But atomic clock, you reference to the same kind of atoms, and that's the beauty of it, because you reference to something intrinsically share the same property, and then you have way higher chance of making that statement that these two clock, they tick it the same way. And that's what you want, what you're looking for, the clock that ticks at the same speed. So your time is, when I share my time with you, you can relate, or you can you know that to very high degree that the time definition is more precise compared to if you using two different mechanical clocks to share time. That's what I
Yeah.
for the difference. Yeah.
Yeah. So I understand and I agree that atomic clocks are better in performance than the classical clocks and other types of ways to measure the frequency or time. But now let's say my question, or maybe my suspicious about the downside, the atomic clocks, they're way more complicated. They're probably just larger in size. Actually, tell me maybe what's the typical size of the atomic clock?
The typical size of the atomic clock varies through time. 20 years ago, you might say that it takes up a room.
Yeah.
A table maybe 4 meter by 2 meter size, occupied by lots of optical components. And because you're trying to address the atoms, and atoms, you need to isolate it from the environment very well. That to be able to achieve that, you need to build a vacuum chamber where your atoms can sit inside of the chamber, where it doesn't interact with the environment too much. Then you can start addressing your atoms very precisely without a disturbance, or like without the perturbation from the environment. But that's 20 years ago, and now people working on this technology, they are trying to improve, trying to shrink the size of the atomic clock, because they are dreaming about one day these things start becoming practical, meaning that people don't get intimidated by the size of this whole apparatus. And they made huge of progress in terms of integration all the technologies, trying to shrink it down the size. And I think, like I say, they are making very good progress trying to turn this technology into the practical level where people will start consider using it.
Yeah, so, and actually, maybe right away my question would be, why this atomic clock still are not a commercially available product? So what's missing?
I think the answer is yes and no. The yes part, the no part is that actually atomic clock is a commercial device already. Depends on what kind of atomic clock you're talking about. Microwave atomic clock that's already a chip size.
Right.
Size. So you can buy a chip which is on the size of maybe 10 euro. Oh no, sorry, even I would say even €1 coin size atomic chip, which gives you 10 megahertz frequency reference, relied on I think some atoms microwave transition. So already there is a chip size scale atomic clock chip you
Okay.
can buy from the market.
But we are still talking about microwave transitions.
Microwave transitions, atomic on microwave transition. And of course, like I said, over the years, people now start getting into like optical frequency transition, and that development is still on its way. And it's already way better than the size of the room occupying all sorts of components. Maybe now it's a size of maybe your desk.
So meter by meter.
Meter by meter, yeah. It's already that level of like scale in terms of the atomic clock on optical transition. It's at that size level. And is there a limit preventing it from going smaller? I don't see it yet. So, but like it's a fast growing field and it's still getting pushed hard by lots of engineers around the world.
So what you're saying is that there is no physical limit, only engineering. So it needs engineering, time, and efforts.
Yes, but careful about this statement because in the process of trying to make it smaller, there would be new problems coming out, and then you're trying to solve it along the way. So engineer, it sounds like you know more or less what's going on in this thing. So right now you just need to throw more resource, and it's no longer interesting from physics perspective, which is not true because like I said, when you're trying to scale something down, there will be new problems coming out. And we learned that from semiconductor industry. When you're trying to shrink down the line width for your semiconductor like device from 120 nanometer to 5 nanometer, I think we've gone through lots of generation of like processing technology development, which there are new problems which people solved along the way to be able to scale it down to that dimension level. So it's engineering heavy, accompanied by lots of new discoveries and inventions.
Yeah.
And yep, so it's I would call it engineering heavy, but not only engineer.
Yeah. And actually, since we started discussing products, do you think that there is a market for these new tools? Because as you said, you already have a microwave clocks, and now you're suggesting, okay, let's do the optical clocks. And it will be a new type of products, and there is a market for these products. Are you aiming for specific requirements?
I'm thinking that there will be a market, but you cannot just trying to compare it with some like commercial electronics product. That kind of market, is it about that? Even though for the ancient, like last generation atomic clock, you don't have that on your cell phone. But does your cell phone need that technology? Yes, you do, because you need a good GPS signal, which your cell phone doesn't need to carry a microwave atomic clock signal, but your cell phone needs to be able to communicate with that microwave atomic clock signal. and you do it through sending signals over to the satellite, or some local like a telecom company base, and then through that you go to the satellite to get that signal. You don't carry that microwave atomic clock signal with you, but you need that. And I'm confident that the next generation atomic clock is going to play the same kind of role. So then when you say that, do you think you have a market for that? Well, as long as your electronics device need my technology in whatever way, then there's a market, because you need my technology. And you so for example, it's like I'm playing some role to you in some aspect, and there's a market. You just need to kind of understand it that way. It's not like you need it in your hand and that's what market, but it's more like whatever you need, whatever technology you're using, whatever applications you're using, you need some input from my technology. Then I call that.
Yeah, so what you're saying pretty much is it wouldn't be useful for practical usage of most of the people, but it will be specific companies which will provide dedicated services, and then this tool will be really practical for them. So it's not like it will be hugely available for public. Let's say you cannot buy it in a grocery store, but for specific companies, it's necessary to build other facilities based on these atomic clocks.
Yes.
Yeah.
Correct.
I agree. And how close atomic clocks, let's say nowadays, to become really commercial products, in a sense, when we can expect them, like 5 years, 10 years?
I think 10 years, 1 decade is a not too conservative prediction. It's going to be in a decade, it will probably happen.
And how many people or companies, research centers right now working on this problem, working with atomic clocks?
Oh, certainly a lot. Industry side, of course, I'm not too familiar, but government side or like research lab side across the world, that's a lot. You can count. I mean, U.S. The institute I'm working in, that's national lab where we are developing atomic clock technology, and then other country like Japan. There's a big group in Tokyo University, but of course they also their Riken national lab. So they are also building atomic clocks, and then country like China, France, Germany, and Netherlands, not yet, but I know that there's soon going to be one, probably.
And this is like now we're talking about a common efforts, or everybody is working on their specific topics, and so there is like a communication, a common ground for this technology to become available, or everybody is working separately?
Certainly, because it's a collaboration like development, because when I develop my clock technology, and if I'm trying to convince you that I make some improvement on my clock, how are you going to so basically there's a good way to do this, that I compare your clock to your clock, and if we are building the same type of clock, in principle they should tick the same way. So like I said, when you have two atomic clock, and because you are relying on the same atom, in principle they share the same kind of property. So my clock in principle should tick the same way like your clock. So they do this type of comparison across the continent. Say, for example, group from Japan have their clock running, send a signal over satellite, and then another group from Germany work on their atomic clock using the same atom, and then send a signal over satellite. Then they compare it that way. So, and this comparison process is to a kind of performance measurement. You're trying to measure the performance of two clocks. In principle, should tick the same way. And it's the type of collaboration in our community, how we sort of collaborate. We're trying to compare our clock to yours and trying to identify any potential contribution which might lead to the difference of our clock, and trying to understand it and trying to improve it in principle. So that I'm just describing one type of collaboration that I'm familiar with. What is that is going on in this atomic clock community, and I believe there are more.
Yeah. And right now we're still talking about academia, and there are lots of research lab, research centers. And do you see that already some people from companies trying to approach you with request for the new atomic clocks? Or right now there is no real request from the companies, even to just participate or partially contribute to the development, creation of new generation of atomic clock?
I know, yes, there are actually a lot, and I can explain you at least from my perspective why. Because, for example, when you mentioned, you asked the question before, like 2 decades ago, atomic clock is like the size of the whole room, which composed of lots of like components important how to make the atomic clock works. And along the progress of like trying to make it compact, make it more practical, make it shrink down the size, you need a lot of engineering expertise. And usually it's the case that people from industry, they know, they possess, they have those kind of expertise better than people from the academia, because maybe sometimes academia people, they're more focused on the principle, but people from industry, they have their expertise. They know how to through the engineering efforts, trying to scale down the size of the whole device. And then for atomic clock, of course, you can think about, you need a vacuum, you need lasers which are locked to stable reference cavity to provide the precise optical frequency so that you can use that light to interact with your atom. I just mentioned laser, vacuum, and people from industry, they use laser for all types of applications, and now they just need to apply their expertise onto atomic clock and trying to find a way to make this laser is no longer a optics table size kind of device. It can be maybe a pointer, size of kind of a device which you can then use for your atomic clock application. And not to mention that there are lots of electronics. You need a lot of electronics to be able to, say, provide some radio frequency for your optical electronics device, and you need you need those electronics to control your experiment. And before, people from academia, of course, they put together lots of different devices which takes up the whole space, a lot of space, say. But now you know already what you need, then, I mean, print circuit board it's not a new technology, and now you already know what kind of signal processing or electronics that you need. You can build a purpose dedicated electronics for your application, and that will largely reduce the dimension of all the electronics that you need for your atomic clock application. People are working on that. Engineering heavy, like I said, but they solve these problems together with academia partner. And like I said, there will be new problems coming along the way, but that's a good team, right? Now you have people, you have partner from academia background, then you have people from industry background, and they are solving problems based on who is more familiar with the principle, and people who is more familiar with like how to solve engineering heavy problems. And then when they join force and trying to solve the problem along the way, especially there will be new problems coming. And then you have expertise from very two separate, different aspects. And then usually you need a team with different background, with different expertise to be able to solve a problem where they to be able to solve a problem efficiently. And what's going on there right now, I would say. So
yeah, and actually what type of expertise you looking in a new employee? Let's say if you want to hire a new person, what's the number one on a few important skills which you're looking for? Because right now, if you're working, if I understand, you're working on the scientific side, but now there is engineering. And if you want to hire a new person, what would you look for?
It's a good question. I have relative little experience of hiring people.
But let's say with who you would like to work on your side.
I certainly enjoyed like working with people. So sometimes you cannot jump into a project which is the complexity level is way beyond your level. But it's not a requirement that you meet that complexity, you meet that level right away in the very beginning when you join the project. Say, for example, if now I'm telling you that I'm going to build a rocket tomorrow, which can go to the Mars, go to the moon. Don't be that ambitious. Yeah. To build a rocket that will go to the top of the mountain, right next to my house, maybe. It's probably more or less right now beyond my capability, beyond my level of the complexity of the project might be too much for me. But if you ask me if I can build a robot which maybe can do some kind of a stupid dance in front of me, like a toy, I probably can do that. And then you ask that, okay, what's the difference between a very complicated robot and very complicated rocket? Trust me, they share some very similar ingredients. Like you need electronics, you need some kind of servo, you need some sort of like a detection scheme which you can then feed back to your mechanism where you're trying to make your robot move. They share the same ingredients. So as long as I have some experience of building a robot, maybe when I join the project trying to build a rocket, I can apply some of my prior expertise on building a robot to the current project where I'm trying to build a rocket that can go to the top of the mountain, go to the moon, go to Mars.
Yeah, so, but now since we are talking about quantum mechanical devices or quantum devices, do you need a specific knowledge in quantum field? Because let's say that you're a very good electrical engineer, optical engineer, but now you're joining a project which is partially, at least maybe partially related to quantum technology. Do you need to know something about quantum technologies?
Well,
Let's say that I want to, let's say
But
that new electrical engineering is joining a project of building a compact atomic clock. Is it possible?
So to build a compact quantum atomic clock, you need some very precise laser, good light source. Then you probably want to have some experience working on lasers. And then, of course, from that, you already developed some experience using the laser. And now the project is about how to make it compact. Same thing applied to actually, for example, for a very precise atomic clock, you need some very good local reference. Say, for example, you need to lock your laser onto a cavity. Cavity meaning like it's a Fabry-Perot signal, a cavity where you can send your light in, and basically light bounce inside the cavity, forming a resonator, and that can give you a kind of like a local reference where, as long as your cavity is stable enough, it doesn't move. Yeah. The length of your cavity doesn't move, and then you can use that to provide to the first level a reference where you can lock your laser onto. And then question is, okay, this is a technology which we use in the atomic clock community, a very good cavity as a reference. And there are two aspects how this technology, where this technology is going, right? How to make it compact, how to make it small, how to make it more precise. And along on the topic of how to make it more precise, maybe now we are considering cooling down this cavity down to the certainly less than 0 degree. We are considering cooling this cavity down to 4 Kelvin. 4 Kelvin, you're hearing me right, 4 Kelvin. So we are considering cooling down this cavity down to that temperature level so we can avoid any thermal noise. And then how to cool down this whole cavity down to that low temperature level? You need some people with some cryogenic system experience, because it's not like you're going to put your cavity inside of the refrigerator in your house and then you call it job done. No, because this needs to be a very stable, nice environment where you still cool down the whole cavity down to that temperature level. That needs some expertise. And you ask, okay, does people from atomic physics, atomic clock community have that kind of expertise? Probably not right in the very beginning when they start considering cooling down their cavity down to that temperature level. But they collaborate with people who have that kind of technology, right? Say, for example, people from superconducting qubits community, they always cool down their device down to that Kelvin degree temperature level. So it's the same technology. Now you just apply it differently. And the task this time is trying to cool down your cavity down to that temperature level. So going back to what I said in the very beginning, you started with some maybe very different project, but you develop some level of experience on certain technology, which might later becoming useful, or we need to use the technology onto the current task we are facing right now, which is always something kind of, you have a good starting point, and then let's now talk about how to apply your prior technology to our current problem that we are trying to solve. So I like to work with people with some prior experience on other type of technology. It's fine, as long as that we both believe that those experience will become useful right now for the project I'm going to work on, and we are going to work together with. So So to answer your question in short sentence, I like to hire people who have some small project experience. Doesn't has to be exactly the same project that we are working on, we are trying to work on right now, but some different project, small project, as long as I know that you develop some experience from your prior project, and I'm convinced that we are going to need that kind of skill, that expertise, and then I will hire the guy.
Yeah. No, I agree that definitely when there is a requirement for the upgrade to a system, you hire a person with a new skill, and it helps you a lot, especially if you don't know much about, you specifically don't know much about this new research line, then a person with a good knowledge can help you a lot. And I want to go a bit to a different subject. When we discussed about creating a new generation of atomic clocks and moving them from research lab to commercially available products, I'm kind of curious, do you think that it's a good place to start a startup? Or maybe there are startups in this field already, because it seems like a good place to it, because right now the technology is relatively mature and ready to, and will become ready to leave the lab soon. And already there is an interest from the industry part. Do you think it's a good place to start a startup right there? And do you know startups already starting at this point?
I do. Say, for example, I mentioned in atomic clock community, we need a very good cavity to lock our laser onto. And the knowledge of how to build a very good cavity, you have lots of, say, for example, you need a vibrational free environment. There are companies which I believe it's a startup from long ago. They are trying to provide you platform, some kind of the platform where you can put your apparatus on top to, and that can avoid any vibration coupled from the environment. That's one example of a good a startup. They developed the technology to provide you a platform where you can confidently decouple the vibration from the environment. So that's one example. To avoid you need a good mirror to build a good cavity. And these days we in our community we are using a type of technology called crystalline mirror, because the material you use for the mirror is relying on some like crystalline coating, which the atomic structure basically gives you a better performance compared to a traditional mirror. So there's a new startup basically building like developing that technology to give you that type of a coating technology, so that you can actually have a better performance for as a mirror which you use for your cavity. That's a kind of a startup. So I believe if there's technology developed which will become competitive, or like the optical clock or atomic clock community needs those things, then there will be a new startup which, because they developed the technology, and then we just relied on their expertise and trying to kind of buy product from them, then we can integrate it into our system. So there will be new startup, and I just gave you two examples.
Yeah, and actually right now, first of all, probably could you not drop your pen? It's a bit.
Okay.
That's one thing. And another point, actually, it seems to me that right now an approach is looking at the atomic clock, which is quite complicated machine, and the startup is useful to pick up one problem which is relatively small in the but in a huge machine of atomic clock, and then improve it. So you as a researcher or engineer don't need to worry about this specific small part of the atomic clock, right? So you just pick up one side and make it good, robust commercial product, and then give it to you, and you already assemble it to the larger machine, to the end product, right? Okay, and I think it's a good place to, like, for the startups to really start doing that. And do you feel like in the future it will be more startups coming, because there are lots of sides of the atomic clock as a machine, and if you can split it in small parts and dedicate each part to the specific startup or company, whatever it is, then you will be just an end user which assemble all these parts together, and then you create an atomic clock, and finally it will be a commercially available product which is really robust and working properly. Do you think this is an approach?
Yep, I think you're right. This is the approach, and you can find already numerous examples from, say, for example, like in the semiconductor industry, they use this EUV device, like an EUV machine, which gives you deep UV light for their wafer processing, and they purchase this machine from a company called ASML, right, from the Netherlands. And for example, and then you ask, okay, ASML, do you think they build everything on their own? No, I think they also buy for example, very good optics parts from one of their partner, which I believe it's Zeiss,
Yeah.
a German company. So, like I said, and there are room for startup to focus on some small aspect of the technology and trying to perfect this thing. And then, like you said, as a quantum engineer, probably I'm more focusing on just relying on their expertise and buying product from them and integrate their product into my device that I'm developing. So, yes.
Yeah, and actually right now maybe another question which is a bit interesting for me is, do you think that right now there are good mechanisms, let's say from government or industry supported mechanism, to provide support for these startups? Because these startups, they're quite risky in the sense that we're talking about quantum technology, very complicated technology, which is not solid yet. So do you see that, let's say, there are mechanisms to provide startups with financial support, and even not just financial support, but even with good people? Because if you start a startup, you have to find funds, people, technology. So do you feel like there are mechanisms to start a startup?
There are, for sure. Say, for example, industry, or I know that, for example, angel funds, there's a lot of accelerator, like in the US, say, for example, Y Combinator.
But specifically for quantum technology, right? It's not just for...
Even specifically for quantum technology, I heard that Y Combinator, they certainly already fund a few, say, for example, biotech company. And that's a different type of technology, which, okay, you don't call them quantum technology. But quantum technology, I think for those investors, I think they are also learning along the way, because you are talking about giving a lot of money to a specifically little group of people who claim that they know the technology to build something which might change the world. So, I mean, they need to know that which group of people they are going to give money to. They need some insight, or like they need to some level of belief. And I think they are learning the way how to pick those small group of people. And quantum technology is just right now, it's fast growing field. And sometimes they're also meaning that there's also lots of fraud out there who overclaim. No, a fraud in a way that, I can make some bold statements claiming that I want to build something which might change the world, which might not be true. But I can still make the claim, right? So do you think I'm going to get the money? Well, if some investors they doesn't have enough experience and they think they buy my words, and then probably they are going to give me money. But to answer your question, there's mechanism where people trying to find a small group of people and they believe their statement and they're going to invest in their technology and give them resource for them to develop their technology, to speed up their development and to and that, so there's a mechanism, but this mechanism doesn't guarantee you 100% successful rate, because sometimes it's just that maybe the technology is just too hard. They need more resource to make it work, and it's not like all the investors they own a bank, right? So or they can print money. No, they have the finite resource. They need to find small group of people where they can believe in, or like they trust. They have vision. They have insights that they know that these people, they will work on this problem with the finite resource that I'm going to give them, and then they can they get the help from the investors. Then they of course trying to deliver what they claimed. So short answer, there's mechanism, and
Nice.
I'm happy to see there are more mechanisms, because these days there are many people get training in this quantum community. They all want to contribute, or like they all develop expertise during their education or during their project, say. And they certainly come up with some interesting new ideas. And the industry starts from having few successful product, that's minimum viable product. And then once those minimum viable product of the quantum technology, they start like growing more and more, then this whole trend will speed up, I believe.
Yeah, I agree. I'm happy to see that this trend of quantum technology is speeding up, and there are even more companies which are working in the research area or with products in the quantum technology world. I really enjoyed talking to you, but I think it's some point we should wrap up, and I think this point is coming. So thank you for joining me today. It was really a pleasure talking to you.
Thank you very much.